All right, now we are live on YouTube for part 2 of lecture 10, where we're going to talk about a few examples involving logic, sets, and Boolean algebra. Let's start from the first review problems. This is a time where you should pause the video and try to solve this on your own. This is probably going to take between 3 or 4 minutes to finish the entire proof if you're careful. All right, what I'm going to do is go through some proof sketch as usual. Okay. So in this case, we are talking about proving two sets equivalences. Remember, if I want to prove two sets A is equal to B, we need to prove A is a subset of B and B is a subset of A. So for simplicity, I'm going to represent the left-hand side to be left-hand side, and then the right-hand side to be RHS to stand for right-hand side. So in order to prove equality, I need to prove two things. One is I need to show left-hand side is a subset of right-hand side. And then for more space, case number 2 is I want to show, it's not case, so 2 steps, right-hand side is a subset of left-hand side. All right, so let's do the first direction. The left-hand side has to be a subset of the right-hand side. And then very much so what we're doing is to follow the definitions. So here we see Cartesian product of set element. So if I have two set element, A cross B, that means we are going to have essentially element, pair of element in the set, X and Y, such that X is in A and Y is in B. Okay, this is another definition we're going to use. So in this case, we want to show the left-hand side is a subset of the right-hand side. So you start with the element from the left-hand side and prove that is an element from the right-hand side, all right? So we say we have X, Y, which belongs to the left-hand side. So left-hand side is A intersect B cross C. So by definition of Cartesian product of sets, right, which is right here, this is a definition, that we will have X is in the first part, which is A intersect B. Oh, let's start, and then Y belongs to the second part of the Cartesian product, which is Y, which is C, okay? So now, because X is belongs to A intersect B, then by definition of set intersection, X belongs to A intersect B, that means X belongs to A and X belongs to B, okay? So because X belongs to A and X belongs to B, and Y belongs to C, then I can pair X with Y. So if I pair X, Y, this belongs to A cross C because we have X is in A and Y is in C. But also because X is in B and Y is in C, when I pair them up, I have X, Y also belongs to B cross C. And this is again by the definition of Cartesian product. Now I have XY belongs to A cross C and XY belongs to B cross C. That means it belongs to their intersection. So therefore, XY belongs to A cross C intersect B cross C, which is equal to right-hand side. So I just proved left-hand side is a subset of right-hand side. All right, so that's one way. What is the highlight of this part of the proof is we start by having an element that belongs to the left-hand side, and then you use the definition of Cartesian product of sets to show that it belongs to the left part of the set, cross the right-hand side of the set. And then you are going to use the property of the set intersection to finish the rest of the proof. So there's two properties, the definition of set intersection, the definition of a Cartesian product. Now let's look at the second part. We want to show right-hand side is a subset of left-hand side. And again, I can start with an element from right-hand side, okay? So say we have x, y belongs to the right-hand side. So that is intersection of two sets. So again, the first thing you're going to use is by using the definition of intersection. By definition of intersection, because the pair xy belongs to two sets intersection, then it belongs to each individual set. That means the pair xy belongs to A cross C, and it's an element in B cross C. All right. Now, if I have already used the definition of intersection, the next one I'm going to use is, if you look at this thing here, this is Cartesian product. So I'm going to use the definition of Cartesian product. Then I have x is part of A and y is an element of C. That is from the fact that x, y, the pair belongs to A cross C. And similarly, we have x is in B and y is in C. Again, it's based on the definition of Cartesian product of B cross C. So now what we have is we have x is in A and x is in B. Then again, by definition of intersection, because x is in A and x is in B, x is in A intersect B. All right. Then what do we have? Then correspondingly, since y is in C, then we have x, y as a pair is going to be A intersect B cross C. Again, this is by definition of Cartesian product again. All right, so this is equal to left-hand side. So what we just showed is right-hand side is a subset of left-hand side. And then combined with part one, left-hand side is a subset of right-hand side. I have showed, then combine 1 and 2, we have left-hand side is equal to right-hand side. That is end of the proof. All right. So at the core of the proof is using the definition of intersection and definition of Cartesian product of sets. All right. So now we have the following statement or proposition, and we want to prove it by a contrapositive statement. So it's asking if to prove that if A intersect B is a subset of C and X is an element of B, then X is not in the set difference between A and C. So there's a few components here. So, and if we want to be careful, we need to think about what is the contrapositive statement here. And let's use P, Q, and R to correspond to each of the statement here. Let's say my P statement is A intersect B is a subset of C. My Q statement is X is element of B. And my R proposition is X is not in A minus C. So the original statement is P and Q implies R. So now we need to write out the contrapositive. It's going to be not R implies not P and Q. But we have to be careful. Not P and Q, you need to use essentially De Morgan's law. This is logically equivalent to not P or not Q. But if the quiz is asking, making the statement of the contrapositive statement, you need to spell it out in the exact form. So what is the contrapositive statement? Is if X is in A minus C, that is not R, then it should be not P or not Q. That means A intersect B is not a subset of C, or the most important part is because I'm taking negation of and, now this become or operation, or not Q, that means X is not in B. So that is a contrapositive statement we want to prove. All right. So if we want to prove contrapositive, let's use a hypothesis first. So suppose X is an element of A minus C. So this is using the hypothesis of the contrapositive statement. Then by definition of set difference, X is in A and X is not in C, okay? Then now we have two cases. So we're talking about X is in A and X is not in C. And specifically, we want to know what is the relation between X and B. So I have two cases. So case number one is when X is in B, and case number two, X is not in B. So if X is not in B, it's the statement that A intersect B not in C or X not in B is already true, because in this case, I assume this part is true. So in a way that for case number two, when X is not in B, I have already proved, because this is true since the second part, which is what's in yellow, is trivially true. So you probably don't have to go further for case number two. So case number one is a little bit involved. It's two more lines of proof. Remember, I assume X is in A and X is not in C. And for case one, I assume X is in B. Because X is in B and X is in A, that means X is in A intersect B by definition of set intersection. Now, also because AX is in A intersect B, and as a second part of the assumption is X is not in C, this means X is in A so that means because there's an element X is in A intersect B but not in C, that means A intersect B is not a subset of C. This is again by definition of subset. So if in the case of X in B, we have showed X intersect B is not a subset of C, which is this part. And of course, when X is not in B, we have already showed trivially the second part. So by those two cases combined, we have proved the contrapositive statement is true. So the original statement is true. right? So this is sort of the detailed proof in here. And I encourage you to go over it carefully. This is how we would expect a detailed proof in the actual exam. So to joggle your memory, there is the following question. What is Boolean algebra? What are the operators? And what are some of the common rules of operations? So the Boolean algebra involving operations of Boolean variables, okay? And you can have operations, which is the operators are things like and, or, and not. And now, of course, there's some special character that is 0 or 1. Those are special characters. What are some rules of operations? If you recall, I have A or 1 is always 1. A or 0 is always A. A and 1 is A. A and 0 is 0. A or not A is 1, and A and not A is 0. Okay. So what are the relations between Boolean algebra sets and propositional logic, and how are they equivalent? So this is a table we're familiar with, right? The operation, Boolean operation, so a lot of and with this, pointing arrow corresponding to set intersection and corresponding to the dot operation in Boolean algebra. Or operation corresponding to set union, which corresponding to and operation. Well, actually, or operation, sorry, it's plus, but it's or operation. And finally, negation corresponding to not or complement in sets and not operation for Boolean algebra. Okay. So here are some of the basic operations. Now we are going to see a particular proof that we are going to use where we want to prove some proposition involving Boolean algebra. We want to show if AB is equal to A, then A plus B equal to B. We want to use Boolean algebra, but we're going to use Boolean algebra equivalence of the set properties as needed. Okay, so what are the equivalences? Again, if I keep in mind is for Boolean propositional logic, I have and. For set operation, I have set intersection. For Boolean algebra, I have the dot operation, which means and. I have or operation for propositional logic, set union, which is or operation, which looks like a plus for Boolean algebra. And then finally, negation in proposition logic is corresponding to not or complement for set operation and not operation for Boolean algebra. So let's try to see what kind of rule can we have. For example, if I want to translate set operation in terms of set intersection, we are going to get, let's say using lowercase a to be the Boolean algebra. And we look at here, so that means A times B is equal to B times A. This is the corresponding translation in Boolean algebra language. So maybe we'll do side by side. Now, how do I translate this rule here? It's going to be A plus B equal to B plus A. So this is the corresponding commutative rule involving Boolean algebra. Let me just be consistent here. And let's do associative rule translation as well. So if I have 3 sets intersect, the first 2 intersect first, and then the third one is the same as intersect the second and third one first, and then intersect the first one. If I translate, again, intersection corresponding to product. So I have A times B times C is equal to A times B times C. So this is a translation. So again, you can translate each of those set properties into properties involving Boolean algebra, okay? But I have not done the proof yet. So as before with proofs of set operations or proof of propositional logic, you can start from left-hand side and then prove that is equal to the right-hand side. So let's start from the left-hand side of the conclusion I want to arrive at. So left-hand side is A plus B. The first thing I can do is I can use a commutative rule, which switch the order of those two. So this is using commutative. And now the next thing, I can use some sort of substitution because there's a hypothesis that AB is A times B is equal to A. So here I'm just going to use substitution of the hypothesis. So because A is equal to AB, I'm going to replace A by AB. The next thing I can do is I can again switch the order of A times B by B times A. That is again commutative rule. And then we can factor out, remember this is algebra, so I can factor out B. This has become B times 1 plus A. And this can be understood as either absorption or just factoring. So let's call it factoring. And the last step, this is equal to B, which is the right-hand side, because I'm going to use absorption. Okay, what is absorption? It's 1 plus A is equal to 1. Okay, where is absorption in here? If I translate this part here, it's going to be A times A plus B is equal to A and A plus B, sorry, A times B is equal to A. So this is the rule of absorption we're using, okay? To be fair, there's actually 2 ways to think about this. So if I directly looking at a part here, I could use absorption rule by substitute A by B and B by A. Okay, so this is absorption, which provide a result of B. What I have done here, I have one additional step where I was doing, so here, this is actually absorption. But if I factor out 1 plus A first, this is really just algebra. Okay. And then what is the next one? Is essentially we're using the rule 1 plus a is equal to 1. So you can write out even more steps. It's b times 1, which is equivalent to b. And all those are essentially algebra. Okay. And oops, we have written out, typed out in more clear way in this slide. Okay, all right, let's look at the next example. Is now we have sets and we're going to draw Venn diagram of the set. Okay, so I have 3 sets A, B, and C. And the first thing we're going to do is A intersect B and intersect C complement. So we are going to put them in general position. This is A, this is B, this is C. Okay, but of course, in order to do that, we can do it by 2 steps, but I'm just going to show it here. First, if I have A, this is B, this is a C. If I were going to take A intersect B, let's first do A intersect B. What do I have? I have this yellow piece. That's A intersect B. But now I want to take this yellow piece and also intersect C complement. What is C complement? C complement is everything outside C. So the final result is taking the yellow area intersect the blue area. Then what we get is the yellow area that lost a little bit of a 3-way intersection. So you get, so that's A intersect B intersect C. Okay. Now let's do the second one. We're going to do A complement intersect B union C. So let's do A complement first. This is A. A complement is everything outside of A. That's A complement. And then we're going to do, so this is A complement. I'm going to do B union C. Again, it's everything in B or in C. Okay, now you want to take the yellow, intersect the blue. Well, of course, I need to specify where my B and C are. So this is A, B, and C. So finally, what do we get? Again, you have A, B, and C. You're going to take all the yellow part, intersect the blue part. So you get something quite interesting. To make sure my yellow is accurate. Okay, so what you get is this orange part. okay? So this is, so of course, I can now ask you the question, are those two sets equivalent? Well, by the Venn diagram, they're not, okay? So this is sort of similar question. If I have two sets A and B, is A minus B equal to A union B complement? Again, the way to do it is to do the Venn diagram. So let's say the first Venn diagram is everything in A, not in B. And of course, this is fairly straightforward. Everything in A, not in B. So it's this yellow region. And now we want to do A union B complement. I'm going to do it by one step. Everything in B prime is everything outside B, and that intersect A. That corresponding to, or that union A, actually, to be, it's not union. So we have everything outside of B, union A. This is everything outside of B first. This is everything outside B. But we're taking union with A, so we actually added a little bit wedge right here. So obviously, those two sets are not equal. So if they're not equal, you need to pick up something that is in the first set, but not in the other set. So a potential location, if you compare the two colored regions, the yellow region and then the blue region, a particular example is somewhere here. So this is a counterexample because X is in A union B prime, but X is not in A minus B. Okay. All right. Oh, that's it for the end of the lecture. If you have additional questions, please come to office hour or use Piazza. Have a good night.